Good afternoon, everybody, and welcome to our Chainguard webinar, Secure More, Spend Less, How Federal Agencies Are Rethinking Software Security. We're so glad that you all could join us today. Before we get started, I'm just going to take a quick minute to go over what we do here at Fierce Software. Fierce Software is a small, woman-owned, value-added reseller. We specialize in enterprise open source software, market-leading DevOps capabilities, and secure data platforms for our public sector customers. Our unique reseller perspective helps us understand your goals and technology challenges, allowing us to offer solutions from our extensive portfolio instead of just a single vendor approach. We set ourselves apart in the reseller market by consistently delivering on our core capabilities. We are an innovation broker to leading technologies, getting our customers access to the smartest people and the best technology available. We are a licensed manager, streamlining customer fulfillment and reducing administrative burdens. Our focus is on customer success, ensuring technical support through vendor-trained and certified professional services. We also provide customer enablement by delivering workshops, webinars like this one, and hands-on events to educate our customers about new features and enhance their team's capabilities. At Fierce Software, we're proud to work closely with our trusted partners to bring innovative solutions to the public sector. One of the ways we're doing that is through our new Fierce Innovation Lab, a secure hands-on environment built with Red Hat, GitLab, and Dell technologies. Whether you're on-site or remote, it's designed to let government agencies and system integrators explore technologies and workflows, all in a realistic, mission-aligned setting. Now I'd like to introduce our speaker for today's session, Philip Brooks. Philip is a senior solutions architect at Chainguard, focused on helping public sector organizations secure their software supply chains from the ground up. With a background as a systems and DevOps engineer supporting the U.S. Department of Defense, Philip brings practical, real-world experiences implementing secure, automated, and compliant infrastructure at scale. At Chainguard, he works closely with federal teams to simplify container security and improve software provenance. Philip is passionate about enabling secure by default environments through modern tooling and open source innovation. If at any point during this session you have questions, please feel free to leave them in the chat, and we will either answer them during or after the presentation. So I'm going to go ahead and stop sharing my screen, and you can take it away.
All right, thank you. It's sound check, right? You can hear me, right? All right. I've got trust issues with my mic, so let's get here. Window. Why can't I find it? There it is, I think. All right. Can you see my screen?
Yes.
Good. Awesome. All right. So you've already introed me, so I don't need to do that. All right. So on today's webinar, we're going to be talking about just open source software and secure containerization. We'll be talking about open source supply chain security, the good, the bad, the ugly, and then really how we can properly build minimal secure container images. And we're gonna go through the good, the bad, and the ugly about that as well. So without further ado, let's get going. So obviously, hopefully, it comes as no surprise to anyone on this call that open source is core to modern application development. Developers are relying on components out there in the open source community to build and package their applications. Now, as you can see, we like to compare it to an iceberg because, I mean, it really sums up that paradigm without having to say too many words. But obviously, I'm going to be a little more wordy because that's what we're here for. But specifically, or to be a little bit more specific, you can see like the top portion of this 2% of source code. That's really what developers out there in companies or the federal government are really writing. They're using open source building blocks to build their open source applications. And that really is the root of the problem. And it's not really a problem per se, but it's really the cause of a significant increase in CVEs and in turn application vulnerabilities today. We're all using the same building blocks to build our software. And while open source is very valuable and it allows teams to innovate at the speed of relevance, these open source building blocks are not always secure by default. They can't always be trusted in their default configurations. Now, let's look at why that is. All right, so what we see here is a typical life cycle, the SDLC, the software development life cycle, from its creation by a producer to its consumption by the end user. And just like any pipeline, attackers can leverage threat vectors, whether it's in the code itself or the build pipeline or the distribution method. They're all looking to gain access or control of one of these methods in order to inject an exploit. Now, you'll see a lot of examples on here like Log4j. I don't know if anybody remembers that. Hopefully you do, because I know it ruined my weekend and pretty much an entire week. I mean, it's used in almost every single Java application as a core component to be able to log, right? It's embedded, and it's that exact principle that everybody's using these building blocks to build their applications that's really leading to this problem. Now, let's talk about one specific. It's on here, XE-utils. All right. So specifically, XE-utils, it really took quite a long time to pull off. It took about 3 years from start to exploit release. And what happened was XE, it was maintained by a small number of people, and it's out there on GitHub. And one day, a person, it was actually a group of people, started contributing and opening up issues and really contributing to open source. Like the core component, or the core, what open source is, it's a group of people contributing. Well, that person wasn't exactly who they said they were. And over the course of 3 years, they earned trust in the program, and they were able to eventually sign off on releases. And in one of those releases was a backdoor. It was one of the first ones they signed off on. They injected a backdoor in it. And now that backdoor wasn't in the code itself. It was actually just in the release that they cut on GitHub. And I mean, that right there is the core issue. I mean, they can build whatever, and you can, I mean, if anybody's used GitHub here or GitLab, Git whatever, right? You can cut a release that you build on your local laptop, and everyone's pulling it. And in this case, XZ, I mean, it's in every single operating system. It's used for compression. So luckily, a engineer was doing benchmarks one night and discovered, I think he was on a Ubuntu system, but a bunch of SSH calls, and like how it was taking a ton of CPU. And he started digging into it, and he realized there's a backdoor here. Now, luckily, XZ, that version of XZ didn't promote it to say stable release, so it wasn't ingested into all these stable versions of everything using it, but it did get into development versions. And that right there is just one example. Now, if we look at libraries and other dependencies, just like XZ, it's really no different than you finding a USB in the parking lot and plugging it into your computer. Like, you're trusting someone on the internet, on the other side, that they have good intentions. And I mean, as we all know, or all should know, not everyone on the internet has good intentions. So it's just like taking a USB out in the parking lot, plugging it into your computer, or adding that code into your application and saying, we're all good to go. Now, I love this depiction of open source and just all really modern application infrastructure these days. Now, at the bottom right, you'll see it says a project some random person in Nebraska has been thanklessly maintaining since 2003. That describes exactly like kind of what XE-utils, but also a lot of libraries and dependencies that are out there. That's this, right? And you can build your entire this really robust and complex digital infrastructure stack, but you're relying on this one little piece down at the bottom that if someone injects an exploit, now they've pwned your whole system. Right? It's like it's a house of cards in that regard, because if you pull out that one little piece in this picture, that whole thing's going to come crumbling to the ground. Now, that's just one piece. We were just talking about the supply chain security aspect of it and how attackers are going to try to look for threat vectors to attack the actual SDLC process. Now, another thing is CVEs. Now, CVEs, they're not going anywhere. And honestly, with the invent of AI, they're, for at least the start, they're only going to get worse, because people are going to find new ways to leverage AI to find CVEs and potentially create CVEs. So CVEs are increasing, they're staying in environments longer, and they're becoming more complex as time and software evolves here. And so this right here depicts a study that was done, I think, by Sonatype, state of the software supply chain. And on average, right, it's showing that CVEs are staying in environments for, on average, this says 275 days, but let's call it 200 plus days, right? More than half a year, CVs are staying in environments. And now what this has caused is a fairly interesting and inconsistent result in government spaces, where some projects in the government, not either, they just have to accept the risk because it's a mission critical system, they're letting these vulnerabilities just ride their POAM until they can deal with it, which, on average, 200 plus days just to get the patch, and then you've got to deploy it. So it tends to expose them to sometimes significant risk over time. And these things, they're not falling off POAMs by themselves, right? They're having to be fixed. Which brings me to what we call the CVE doom cycle. All right. Now, we coined a phrase here that start left or shift left. And I'm sure everyone by now has heard the term shift left, right? Where you're going to shift security principles further to the left, further to where the development is happening. Well, it's not as easy as it sounds. And I think over the past couple of years, there's really been a effort to make this happen and to really try. But what teams, I believe, are finding is that shifting left is hard and it slows things down. And when you're trying to get something deployed and working, you usually forego a lot of these security gates and just to get the job done and get that thing released. Now, if we look at this diagram, we're looking at the top part here. So today's state, the CV doom cycle. Now, if we're talking specifically about images, which we've been talking a little bit about a lot of things, but let's start talking about container images themselves. When a developer or your system engineers go and you pull an image out from Docker Hub, Quay.io, or wherever out there from the public internet, developer pulls it and they scan it, right? It goes into the security scan or it goes into maybe a production environment or whatever, right? You do your due diligence, you scan to see what the threat posture is. And a lot of times you're getting hundreds or dozens, hundreds, or maybe, I've seen several hundred CVs from a single container image. And now you've got to work on triaging, patching, and trying to figure out, writing mitigation statements, trying to figure out, all right, how can we deal with these? All right. And then the next minor release comes out and you want to get rid of CVEs because they've been patched. They've been patched now. Well, that process just starts all over. And it's just this never ending loop of scanning and triaging and evaluating risk for CVEs that, we'll get into this later, sometimes aren't even relevant. And so my cat here, or a cat. So like what ends up happening is, all right, we knocked one off the list. Now we've got several hundred to go. And on average, what we're finding is that federal programs are spending annually 15,000 hours, man hours, to deal with this never-ending cycle. And now that's obviously not a single person, because there's multiple people in the security stack, as it were. And so like it's several people's full-time jobs, and it's not a solvable problem when you have several hundred or even a couple thousand CVEs writing your POAM, and then you've got to write mitigation statements for them. And it's not a solvable problem. So now let's look at the cost, like one of the things was what secure more, spend less. Let's look at the cost of this process, really, and trying to do this process yourself. On average, we'll say 3 to 6 hours per CVE, and that includes several things from pulling, assessing, patching, and triaging and mitigation statements, etc. Right? So it's 3 to 6 hours on average. Some are harder than others. And then you've usually got a 200 CVE backlog. And then, I mean, as anyone who's lived this, they've realized, okay, I pull a new patch, I got rid of some CVEs, but now I have new ones. All right, so now you've got more new CVEs. You've knocked some off the list, and then 15 to 30 minutes for reporting. And what that adds up to is a lot of time and a lot of money spent trying to solve this doom cycle. And then if we throw FIPS into the mix, right, that's just even more time. I mean, you've got to go find the expertise. You've got to create build pipelines to add FIPS or validate FIPS, and then you've got to do testing, right, to make sure that FIPS is actually working and the application's working now that you've added FIPS. Again, it's just a lot of time. It's a lot of money, and the total cost of ownership of you trying to solve this problem yourself is high, and that's really what Chainguard was meant for. Now, let's talk a little bit about how we create zero CVE images, and really the process, because I think you guys you're here to learn, and I want to provide more than just a doom outlook of what open source is, and because that's not my intention. Now, let's jump into at least what you shouldn't do. All right, at least the wrong way of doing things from the start. There's a process out there. It's known as debloating or slimming a container image. And the reason why this is wrong, and it actually just creates new problems for you, is when you go and you take an image that's out there and you start removing things, the first thing is you're likely going to be breaking the supportability of these images, as well as breaking how other solutions in your environment look for security risks. And like, if you want to, we can get into that more if you guys want. But happy to talk offline. Connect with me on LinkedIn. We can talk about it. The second thing is the provenance of a lot of this, right? The packages and the things inside of the image. Well, those may be static files or metadata. It's not necessarily accessed by the application. So when you go and do a slim and your application doesn't touch those files and you just delete it, now you're removing artifacts that help tie packages and software back to the maintainer and where that code came from. And we call this dark matter. And you're potentially just introducing new threat vectors that you don't even know are there, or you can't verify the provenance and integrity of the container image. So I wanted to start that before we get into kind of the meat and potatoes, because this is the wrong way of doing things. Let's talk about the right way of doing things. But first, let's talk about really the problem that leads to at least CVE bloat inside containers. And it really comes down to the dependencies inside of container images. So there's a couple different type of code level vulnerabilities. All right. The first one is you've got a block of code. It's in your application, and say you're not doing proper input validation, right? You've got a CVE that's present, and it's in your application. You own it. The next is I'm importing a library. I'm importing a dependency we'll talk about this in more detail, but that's actually what's vulnerable. Not my code that I've built, but I've built on top of this other thing that I'm using as a dependency, and that's what's vulnerable. All right, and then the third is actually what's what we call transitive dependencies. It's dependencies of dependencies, and there's a CVE living deep down, right? And the core problem is you lack the control to actually be able to patch. And that's because your application, which is at the top here, well, it's waiting on the maintainer of dependency one to pull in, or to one patch and pull in the patch from dependency two, or the dependency of the dependency. And so when you get into these more complex applications such as this, you can see there's several dependencies, and then you've got to wait on the maintainer of, well, one, this to patch, which is usually fairly quick, but then you've got to wait on the maintainer of this to patch, and that this maintainer has to wait on this one to patch. And it ends up being this cascade of waterfalls of just waiting on other maintainers to patch things. And that's really what contributes back to the 200 plus days that a CVE is active in an environment, or active in open source. It's because of that process, the waiting process. Now, let's talk about a little bit more detail. Another thing, which is instead of just dependencies causing CVEs, there's also something known as bloated image or bloated base images. All right, so it's really all about your base image in terms of starting from a secure point, right? Starting left versus shifting left. And you'll notice that there's a lot of gray dots up here, and there's some red in some of those dots, right? Well, these are unnecessary components that are being inherited from the base image, or that the open source project is using to build on top of. So in this case, a Python application, it's building on top of, say, just the Docker Hub Python image, and it doesn't need all this, right? Like defense in depth, if you're not using it, why is it there? And so that's also what contributes to a lot of the CVEs inside of open source today. All right, to kind of drive this home a little bit more, let's talk about the base images and things like that. Exactly what I was just describing. So here you can see we're scanning the Python latest image. So it's the latest build, right? It should be the cleanest. And we're scanning it with Gripe. Open source scanner, Trivi and Gripe usually have very similar results, but it's finding a critical CVE that's present in zlib. All right, well, let's dig into this a little bit. So it's a dependency in zlib that's called minizip, and it's a buffer overflow vulnerability. However, to be exploited, a couple conditions have to be met, right? And since these are not met, it's technically a false positive, right? And that's why it's marked as won't fix. However, there is a patch available in minizip, or the new version of zlib, but why should I? You don't necessarily have to upgrade to be able to pull in the patch. But since it's a false positive, they don't really care about it. Now, in order to figure all of that out, I would have to triage and figure this all out to be able to write up a mitigation statement and say, well, yeah, it's popping, but it's not applicable. And that's just a lot of unnecessary time spent, tying back to all that time and money that's just kind of, for, I mean, lack of a better term, being wasted, even though there's technically a patch available out there. So what if there's a better way? All right. And this is kind of how we do what we do. And how, like, the proper way of doing things. We've mentioned how we shouldn't do it and the problem, but how should we do it? So first, start from a secure minimal base image, such as Chainguard base, which is a distro-less base. So it's very minimal. And then you build all of these dependencies from source code. So that allows you or us to be able to pull in the necessary patches, right? So if there's a CV back here, I can patch this and start moving back up the chain all the way the tree and patch as you go, right? And you never add any unneeded components in the first place, because I'm not using a bloated base image that has a bunch of things that I don't need, right? And then this is going to scan clean or close to clean if there's CVs present here, right? That's the proper way of doing things. Patch dependencies as you build on a slim, verifiable, declarative distroless image. All right, just checking the chat, making sure there's no questions. I mean, if you have questions, please throw them in the chat. I should have probably said that at the start. I'm monitoring it as I go, so if there's questions pop up, I'll answer them. So you can see if we scan the Chainguard Python latest image, there's no CVs, and it's because of that process. We're starting from a minimal distroless base image. We're adding only the packages that are necessary, and we're patching the dependencies as we build from source, going up the dependency tree. And what that also tends to leave us with is a much smaller image, right? Obviously, if we look at the right-hand side here, we're hitting the Python image that's out there on the internet, on Docker Hub. All right, and on average, it's carrying about 202 CVEs and is about 350 megabytes. Well, ours is 0 CVEs. You can see there was a little blip back, about a month ago, where a CV popped for a couple of days, but then a patch was available, and since you're rebuilding all the dependencies, we're able to pull in that patch. But the actual size is only 22. I mean, so there's just so much bloat in that base image, and then what your developers are going to do, or what potentially, if there's developers on the call, what you're doing is going and grabbing that Python image from Docker Hub, and you're adding your application, which has its own dependencies. And now, not only is your size high, but your CVs are going to start climbing as you go. All right, the next thing that's important is during your build compilation, it's important to analyze things and build in a secure fashion. So one thing that you can do is leverage the OpenSSF's secure compiler options hardening guide and use secure compiling flags at compile time, right? As well as doing malware analysis on the code and the artifacts themselves. We developed something called malcontent, and this is a screenshot of it right here. But basically what it does is it's basically doing heuristics, and it's looking for patterns in the code and the application. And it's looking for things like injection possibilities and just patterns. It uses, I think, 14,000, it's somewhere around there, but Yara rules to be able to detect these patterns. And one case study is the most recent rsync vulnerability that dropped in early 2025. We were actually remediating that before it was even publicly disclosed, because we were using these hardened compiler flags. So proactively building things in a hardened and secure fashion. All right, so we've talked about a lot of things here. We've talked about really open source problems. We've talked about the way to properly build container images. Now, what about the migration or the adoption of these images? You may say, well, it sounds like a lot. Like, how can I migrate? It sounds like that's going to be a fairly heavy lift. Well, not necessarily, right? A lot of times, it's just a matter of switching out that base image. If you switch out that base image, that counts for, I've seen sometimes 750 CVEs or even higher. That's already knocking several hundred CVEs off the plate just by changing a one line in the Docker file. So you can see here, we're changing it from, instead of using just Python latest upstream, use the Chainguard version, right? Use a distroless base, add Python. And then the next iteration, you could add FIPS, right? And make sure your application runs on FIPS. And then the final stage should be a multi-stage build. And now let me explain the differences there. I should have made a slide for it, but I didn't. So each one of our images, there's a dev and say production variant. The development version is going to have things like package manager, so you can just pip install. Where the production image, it's just going to have Python in it. All right. So what you do is a multi-stage build, utilize a dev variant, and then copy the things you need out of that dev variant into the production image. So create like a virtual environment, copy from dev as builder, and then put that into the production image. And what you're going to be left with is a much smaller image. So like our example here, we went from 602 packages down to 174 because we don't need pip anymore because we're not installing anything. That's an additional threat vector. We don't need a shell, right? Security best practices. If you're going to throw something in prod, you don't need certain things, which brings me to here. The goal. All right, so upstream images, again, they're bloated, single stage Docker files. They're just leaving things around. Default root credentials and non-FIPS, right? I mean, those are just some things. Well, if you move to, say, a secure base, multi-stage builds, fixing those security best practices like not running as root and specifying a user, and FIPS is a nice to have, especially if you're in a federal space. But at least the first three, like you're going to be on a much cleaner foundation than you would be without this. So you can see my little cat here. He's just vibing, no stress, because you don't have to do that CVE doom cycle, right? Like all that's done. Like if a CVE pops, it might be one or two. It's much easier to write a mitigation statement for one or say even 10 CVEs than it is for say 100 or 1,000. Much easier. So I kind of flew through that pretty fast. But the goal here is not to alarm anyone or suggest that open source is inherently unsafe. I want to make sure I drive that home. That's not the case. It's quite the opposite. Open source is powerful, but the way it's delivered and consumed introduces real risk. And as the industry struggles to keep up with the relentless flood of CVEs, a challenge only likely to intensify with the advent of AI, it raises really a critical question. Isn't there a better way to consume open source? Right? Whether it's building from source or leveraging something like Chainguard. While it might seem possible to DIY a secure pipeline, it's possible. Scaling that effort, however, it tends to be a different story, right? What tends to happen is in your environment, you're not just using one piece of open source, you're using several, dozens, sometimes more. And to scale that out and rebuild everything, including all the dependencies, which is kind of an exponential curve, it's a lot. And so that's why I believe it's far easier and safer to consume pre-built container images from Chainguard. Are there any questions? I don't see anything in the chat. Y'all been kind of quiet. Any questions? Is there anything you want to dive deeper into? I know we had an hour scheduled, but I kind of went fast. I'm not seeing any questions, Jody.
Okay, well, thank you so much, Philip, and thank you everybody for joining us today. If you have any last minute questions, please feel free to put them in the chat. We will be sending out an email within the next 24 hours with the video recording of this session, so you can revisit anything at your convenience. We really appreciate you spending your time with us today, and we look forward to seeing you all at our next webinar. Have a great rest of your day, everyone.